Alright, so going back to ordinary differential equations that are non-homogeneous with constant coefficients like this one, where we have a function, in this case it will be a function of time, because the Laplace transform essentially is just an integral transform that takes a function of time and transforms it into a function of frequency. So frequency in mathematical terms is usually denoted by s. So what we're doing is we're transforming that function from the time domain to the frequency domain, and that is what this Laplace transform is doing. So just to illustrate what this is going to do is essentially, let's say you take a function of t, applying the Laplace transform is essentially multiplying that function by this function here, exponential function of e to the power of minus st, and this portion of the integral, which is always present, is called the kernel of the integral. And basically this is the unilateral or the one-sided Laplace transform because we're only taking it from 0 to infinity. The double-sided Laplace transform would actually go from minus infinity to infinity. And the main difference in that is that because we're working with time in most cases, because we care about dynamical systems in real time, time can only start from 0. So that's why we use the one-sided Laplace transform to solve those problems. Now, we can apply the Laplace transform to a whole ordinary differential equation. And what that's going to do is going to transform it into an equation in the frequency domain. And then if we apply the inverse Laplace transform to the whole equation again, we get the solution to our differential equation. And that's quite a neat property of it because there are a lot of results and tables on Laplace transform pairs and inverse Laplace transforms. So if we have any functions that are very common, we can simply use tables to find the solutions rather quickly. So just to illustrate how this works, I'm going to show you what happens when we want to take the Laplace transform of the function e to the power of at. So in that case, what we will get is integral of 0 to infinity. The function is e to the at times e to the minus st with respect to time. And this is the same as saying integral of 0 to infinity of e to the power of minus s minus a t with respect to time. And then we can set this equal to, we just integrate, it's a very simple integration. So that's just going to become minus 1 over s minus a e to the power of minus s minus a times t from infinity to 0. And that's going to be what? Well, we know we substitute t for infinity in the first case because this is a negative exponential. We know that that's just going to make the whole term go to 0. Minus the term when t equals to 0. So if we put 0 in here, this becomes 1. And then we just have minus 1 over s minus a. So the whole thing becomes 1 over s minus a. And in general, the way that you can check that your Laplace transform is correct is you need to get a function that is a function solely of the frequency. If you have any t terms in here, you know something went wrong because it should be a function of frequency and not time. And usually with Laplace transforms, you will get a fractional function like this. So you will have something in the denominator. And in the next video, we're going to see what happens when you try to invert a function like that. But for now, I'm just going to introduce some of the properties of the Laplace transform that are really important and very useful to know. So I'm just going to get rid of this screen because I'm going to need some space to list all the important properties that we need to work with. So the first property of the Laplace transform is going to be the following. So we're going to have Laplace transform of a function where you have some constant times t is going to be equal to 1 over a times the function, this would be the Laplace transform of s over a The second property is going to be, let's say we have a product of functions, in this case just t to the power of n times function of time. This is going to be equal to minus 1 over n times f to the power of n. Not f to the power of n, sorry, this should actually be the nth derivative of that function of frequency. So nth derivative of f of s. Now the next property is going to be the property of linearity. So we're going to have a sum of functions like this, and this one is quite important. We're going to be using it quite a lot. Let's make another function of time here, and this is going to be equal to a times Laplace transform of f of t plus b times the Laplace transform of g of t. And hopefully that's a little bit intuitive. And the reason the constants come out is because the Laplace transform of a function times the constant is the same as this. So that's another property that we need to remember. And now the next two properties, well, that are going to be part of a more general case, is what happens when you take the Laplace transform of a derivative of a function. So let's say we have the Laplace transform of f dash or f prime of t. This is going to be equal to s times the function of frequency fs minus the function of time at time 0. So that would be the initial value of the function. And then what about the second derivative? Well, the second derivative is going to be a little bit similar, but it's going to be extended by one term. So that's going to be f double prime, and this is going to be equal to s squared f of s minus s times f of 0 minus f prime of 0. And you can try and derive those yourself. There's a whole derivation behind it. I won't go into detail into it because what we care about is knowing, okay, so that's the Laplace transform of a first derivative, and this is the Laplace transform of a second derivative. And now that we have those tools, we can actually proceed and try to solve an ordinary differential equation using those methods. But before we move on to that, in the next video I'm going to cover the method for inverting the Laplace transform, because we need to get from the frequency domain back to the time domain if we want to express our solution in terms of time.